Chapter 25, Statistical Thermodynamics. Section 25.6, Heat Capacity. The isochoric molar heat capacity is denoted by C sub Vm. It's equal to delta U sub m over delta T. U sub m is the molar internal energy. And we have this V in the subscript that denotes isochoric condition. The molar internal energy is the internal energy of 1 mole particles. Therefore, we have this equation: the molar internal energy is equal to the Avogadro constant times the average energy of one particle. We now evaluate the average energy of a particle at temperature T. It's the sum of the average translational, rotational, vibrational energies plus the average electronic energy. The first three terms, translation, rotation, vibration, they are the motions of the nuclei. The last term is the electronic energy. That includes the nucleus repulsion in here for convenience. For monatomic gases, the rotational energy is 0. The vibrational energy is 0. The average translational energy is 3/2 kBt. And this is the electronic energy. So we have this sum that contains only two terms: the average translational energy and also the ground electronic state energy. Monatomic particles do not possess any rotational or vibrational energy. We can easily get the isochoric molar heat capacity for monatomic gases. We just plug in this equation. It's delta U sub m over delta T on a constant volume condition, and that's N sub A times delta average energy over delta T, constant volume condition. And over here, the electronic energy does not depend on T. This is just the ground state electronic energy. I'm assuming the electronic energy spacing is much greater than kBt. So this part is independent of temperature. And over here, we just get 3/2 kb. 3/2 kb times the Avogadro constant is 3/2 R. So the isochoric molar heat capacity of monatomic gases is 3/2 R, assuming ideal gas behavior. It's just because when we derive this part, when we derive the average translational energy, we assumed ideal gas behavior. The isobaric molar heat capacity of monatomic gases is simply 5/2 R, just because CPM equals CVM plus R for ideal gases. The isochoric molar heat capacity CVM is delta U sub m over delta T on a constant volume condition. The molar internal energy is the sum of the 1 mole particles divided by mole, and therefore the molar internal energy is simply the Avogadro constant times the average energy of one particle. The average energy of one particle is the sum of the translational, rotational, vibrational energies of the nuclei. And also, we need to include the electronic energy as well. And again, over here, in this electronic energy, we include the nuclear repulsion for convenience, so that we have only 4 terms here. Otherwise, we'll have another term, which is the nucleus repulsion. Now let's look at diatomic molecules. Well, when you have diatomic molecules, we have rotations, we have vibrations. Therefore, we have 4 terms over here being non-zero. The first term, translational energy, on average 1.5 kBt. Rotational energy 1 kBt. Because really it's only 2-dimensional rotation. The rotation about the molecular axis does not count. vibration, 0 point vibration energy plus the thermal correction. We got this thermal correction from the section on vibrational partition function and energy. And over here, it's just epsilon 0 electronic, which is just the energy of the ground electronic state. We can combine the first two terms, and we get 5/2 kBt plus 1/2 h nu, 0 point vibrational energy. This is the vibrational thermal correction, and over here this is just the ground electronic energy, which includes the nucleus repulsion. We can then get the molar isochoric heat capacity. It's simply delta U sub m over delta T, and then we just look at this. We take its first derivative with respect to temperature, and then multiply by the Avogadro constant. And from this, we get 5/2 R, and this term disappears because this does not depend on temperature. This term also is independent of temperature. So we need to take the derivative of this part over here with respect to temperature, and then multiply by Avogadro constant. For most diatomic molecules, we'll just get 5/2 R, or 2.5 R for most diatomic molecules, unless you're looking at molecules with very low vibrational frequency, and then this part can be significant. So for example, if we are looking at chlorine 2, I think chlorine 2 has a very low vibrational frequency, and therefore its molar isochoric heat capacity is going to be much larger than 2.5 R for that reason. So really we need to look at this and see if this part can be neglected. If you have a vibrational wave number higher than 400, 500 wave numbers, this part can usually be neglected. For linear polyatomic molecules, again we have four parts: translational, rotational, vibrational energies of the nuclei plus the electronic energy. And since it's linear, this part is 1.5 kBt, this part is just 1 kBt, together 2.5 kBt. Vibrational energy, since it's linear, we have 3n minus 5 vibrational modes. For each vibrational mode, we have the sum of the 0 point vibration energy and the thermal correction. And finally, electronic energy of the ground electronic state. Again, we're assuming the excited states do not matter, just because usually the electronic energy spacings are much greater than kBt. So most molecules, nearly all of them, are in the ground electronic state. Again, n, this uppercase n is the number of atoms. We have a total of 3 motions, and we need to subtract the 3 translational motions, 2 rotational motions. Therefore we have 3n minus 5 vibrational motions. For nonlinear polyatomic molecules, we have almost the same expression, except for nonlinear polyatomic molecules, now there are 3 rotational modes. So we have 1.5 kBt for translation and also 1.5 kBt for rotation. Together it's going to be 3 kBt. So look at the difference here. It goes from 2.5 to 3 because now we have 3 rotational modes versus only 2 rotational modes. We do have one less vibrational modes. It's 3 and minus 6 now, because we have 3 trans and 3 rotations. Therefore we have 3 and minus 6 vibrational modes. And again, electronic energy. At 0K, the average energy of nonlinear molecules is simply the sum of 1/2 h nu plus electronic energy. Why? When temperature is 0, this is 0. When temperature is 0, this exponential function is infinity. 1 over infinity, that's 0. So we'll just get the 0 point vibrational energy plus the ground electronic state energy. The average energy of linear molecules is similar. It's just we need to change 3n minus 6 to 3n minus 5. That's the only difference. Now again, let's review this monatomic gases such as helium, neon gas. The average energy is 3/2 kBt or 1.5 kBt plus electronic energy. The molar internal energy is just Avogadro constant times this. We get 1.5 RT plus the Avogadro constant times the electronic energy. The isochoric molar heat capacity is therefore just 1.5 R, because this part does not depend on temperature. The derivative of this part is just 1.5 R. Really easy. Again, we assumed ideal gas behavior over here. When we derive actually the average translational energy, we did assume the ideal gas behavior. And for ideal gases, CPM is CVM plus R, so CPM is 2.5 R. Now let's look at a few examples. The values of the isochoric molar heat capacity of helium, neon, argon, they're all 12.47 joule per mole Kelvin. The CVM of atomic gas of a metal, such as mercury or sodium gas, is also 12.47 joule per mole Kelvin. It's not a coincidence. It's just because 1.5 R is 12.47 joule per mole Kelvin. R is 8.31446. The molar isochoric heat capacity of monatomic gas is only 1/2 in one of the 3 dimensions, but we do have 3 dimensions, so it becomes 1.5 R. Well, later we will learn this. Rotational molar heat capacity of a molecule is also 1/2 R for each rotational axis, about each rotational axis. For linear molecules, we have 2 rotational axes. Their rotational CVM is R. But if we have nonlinear molecules, we have 3 different rotational axes. Therefore, their rotational CVM is 1.5 R. Again, each translational molar heat capacity is just 0.5 R. Since we have 3 dimensions, the total is 1.5 R for translation. For rotation, it depends. Linear molecule, we have only 2 rotational motions. It's going to be R. For nonlinear molecules, we have 3 rotational motions. Therefore, its isochoric molar heat capacity is 1.5 R. For diatomic molecules in the gas phase, again, we have this expression. The average energy is, over here we have the average translational and rotational kinetic energy. Again, both translation and rotation are included in here. We have 1.5 kBt for translation and 1 kBt for rotation of this linear molecule. The second and third terms together are vibrational energy. 1/2 h nu is the 0 point vibrational energy, and this is the thermal correction of vibrational energy. Finally, electronic energy. The molar internal energy is simply the Avogadro constant times the average energy of a particle. So we get this term, 2.5 RT plus the Avogadro constant times the vibrational energy plus the electronic energy. So CVM is roughly 2.5 R if you just look at this term. Because h nu does not depend on temperature, electronic does not depend on temperature. Over here, although this does depend on temperature, the dependence is usually small, as long as your vibrational wave number is more than 400, 500 wave numbers. So usually it's just 2.5 R. And again, we assumed ideal gas behavior, so CPM is equal to CVM plus R, 3.5 R. Here are a few examples. The CPM value of H2O2N2 are 28.8, 29.4, 29.1 joule per mole per Kelvin at room temperature. And they correspond to roughly 3.5 R, 3.5 R, 3.5 R. The CPM of diatomic molecules of much heavier elements may be notably greater than 3.5 R because of the more significant contribution from their low frequency vibrational mode. For example, the vibrational wave number of CO2 is only 560, and then the CPM of chlorine 2 is 3.98 R, so it's more than 3.5 R. But still, I think 3.5, 3.98 are fairly close to each other. For diatomic molecules in the gas phase, we have the molar internal energy, which is the molar translational and rotational energy over here, 2.5 RT, and then Avogadro constant times the average vibration energy plus the average electronic energy. The vibrational thermal correction is this. The corresponding thermal correction to molar heat capacity and consequently molar isobaric heat capacity of diatomic molecule is this. We'll have to take the first derivative of this guy with respect to temperature. So it's really complex. We have negative n sub a times h nu over this guy squared because this is on the bottom, and then we use chain rule. We get the first derivative of this, which is simply e to the power of h nu over kBt over here. We copy that here, and we copy the exponential term h nu over kb from here, chain rule, and then negative 1 over t squared because this t appears on the bottom. Putting everything together, we get r times h nu over kBt squared, and on the bottom e to the power of h nu over kBt minus 1 squared, and then times e to the power of h nu kBt. We see h nu over kBt here, here, and here, so maybe we should pre-calculate h nu over kBt first and then plug it in. Let's look at chlorine. Chlorine has a wave number of 560 wave numbers. The experimental value of CPM is 3.98 R. It's not 3.5. It's more than 3.5. It's 3.98. Now let's make some theoretical prediction. Over here, let's compute h nu over kBt for chlorine 2. We can plug in this wave number to get frequency. From frequency, we get h nu over kBt. It's 2.7 at the room temperature. Alright, and then we evaluate this whole thing a lot, and it's r times, this is 2.7 squared, e to the power of 2.7 minus 1, and then squared, and then over here e to the power of 2.7. We get roughly 0.5 R. So the calculated CPM of chlorine 2 is 3.5 R without the vibrational thermal correction. And over here, this is vibrational thermal correction together. We predict its CPM is 4 R. Now let's look at the experimental value, 3.98 R, really close to each other. So for chlorine 2, it's better to look at the vibrational thermal correction here for a more accurate isochoric molar heat capacity. For linear polyatomic molecules in the gas phase, again we have the average energy here. This is the average translational energy plus the average rotational energy. So 1.5 plus 1 kBt. And over here we have 3n minus 5 vibrational modes. And we have 0 point vibration energy plus the vibrational thermal correction. And then electronic energy. Molar internal energy is Avogadro constant times the average energy. We get 2.5 RT plus the Avogadro constant times the average vibrational energy and electronic energy. Now let's look at CVM, CPM. CVM is the first derivative of this whole thing with respect to temperature. The 0 point vibration energy does not depend on temperature. The electronic energy does not depend on temperature. This term, although does depend on temperature, usually the dependence is small. So roughly the molar isochoric heat capacity is 2.5 R. CPM is R plus CVM, so 3.5 R. But if you have vibrational modes with small wave numbers, or if the temperature is pretty high, we do need to look at this term, the thermal correction, because this term can be more significant with small wave numbers or high temperature. Alright, in that case, well, CVM is greater than 2.5 R, CPM is greater than 3.5 R. So we actually studied chlorine 2. We see that CVM is roughly 0.5 R greater than this. CPM is also 0.5 R greater than this. Now let's look at nonlinear polyatomic molecules in the gas phase. Well, this time the average translational energy is 1.5 kBT. The rotational energy is also 1.5, so together you see 3 kBT here. This is the difference between nonlinear and linear. For linear, you have 2.5 kBT here. For nonlinear, 3 kBT here. We do have one last vibrational mode in nonlinear molecules. It's 3 and minus 6 versus 3 and minus 5 for linear molecules. And over here we have the vibrational energy. This is the lowest possible vibrational energy, and this is the thermal correction to the vibrational energy. Finally, electronic energy. And then we multiply everything by Avogadro constant. We get 3RT plus Avogadro constant times the average vibrational energy plus electronic energy. And then this is the molar internal energy. The isochoric molar heat capacity is delta U sub m over delta T. It's roughly 3R. Comes from here. And CPM is roughly 4R because CPM is R plus CVM. This part does not depend on temperature, and this part does not depend on temperature. This part does depend on temperature, but usually the dependence is fairly small, unless you have small wave numbers or very high temperature. And then we need to worry about this part, because this part can depend on temperature significantly. And then we need to kind of just include the derivative of this part with respect to temperature. Here are a few examples. The values of CPM of ammonia and CH4. They are both greater than 4R. So for ammonia, it's 4.22R, greater than 4R. For methane, it's 35.7 joule per Kelvin per mole. It's 4.29R, also greater than 4R at room temperature. So at room temperature, the isobaric heat capacity of ammonia and methane are both greater than 4R, just because of the contribution from the thermal correction to vibrational energy. And usually we look for the smaller wave numbers. In ammonia, in methane, we have vibrational modes that correspond to the change of the dihedral angle. And usually when you change dihedral angle, it does not require a lot of energy. That means we have small vibrational wave numbers. And actually those small wave numbers make the most contribution in here. They make great contribution to the vibrational thermal correction and also vibrational heat capacity. As a result, the CVM of ammonia and methane are greater than 3R. How much greater? Well, I think their actual isochoric molar heat capacity are greater than 3R by 0.22R and 0.29R respectively. And in turn, their CPM are also greater than 4R by 0.22R and 0.29R respectively.